Thank you. Well, Jorn and I will both be speaking about counting Matroids, and Jorn will be doing the difficult stuff, as we agreed.
In view of your advanced age.
Yeah. Because the thing, so Jorn is going to speak about our last result, which builds on earlier work, and we thought instead of having one long talk, doing a lot of preparation, I will do this preparation in historical context, right? So here goes. I'm really going to start from scratch. And I can see that at least one person is very happy with that. So the issue is, how many matroids do you have on a ground set with n elements? And of course, to make that question make any sense, you have to fix the ground set. So now our ground sets will be just the numbers 1 to 2. And yeah, our notation is mn for all matroids on n elements, mnr for the number of matroids on n elements with rank r. So the very first thing that occurs to you when you do this, and this is just to get an idea of what kind of numbers we're talking about, is consider that a matroid is determined by its independent sets. And the independent sets are a subset of the power set of the ground set. So if you just consider that the number of subsets of this power set is 2 to the 2 to the n, well, that's your upper bound. That's an easy upper bound. Now, as you can see, most of the action is happening up here in the exponent. So I'll usually end up with a statement about the logarithm of the number of matroids from n elements in this talk. So this just brings the exponent down a bit. So our first upper bound is 2 to the n. 2 to the n for the logarithm of the number of matroids from n elements. So this is not the best you can do. I mean, clearly you're not even using that your object is a matroid, right? You're just counting all subsets of the power set. That's terrible. So how can we use that we have a matroid? Well, we can consider the fact that the matroid is also characterized by its bases, and this set of bases comes from a smaller set, namely all the subsets of cardinality R of the ground set. And so then you get that the number of matroids on n elements of rank R is at most 2 to the power n choose R, and n choose R is at most n choose half n, and so this gives you a bound like this. So this upper bound here you get from just a well-known upper bound on the monomial coefficients. It's about 2 to the power n divided by root n, and I think the constant is square root of 2 over pi. But let's not bother with, this is not the best bound we're going to get anyway, so let's not worry us with those constants. Now one thing that happens here is I'm bounding all the matroids by summing over the different ranks, and so I'm being very lazy making this upper bound, because I'm just bounding all these by 2 to the power n choose n over 2. But it's not actually going to matter for the quality of this upper bound, because this n plus 1 that you get by summing just becomes an additive constant of log n plus 1, which is just nothing compared to this exponential thing. And this happens more than once. It's often when you take the log of some sum, it's the worst thing that completely dominates the bound. And well, we'll see this more often as I get to more complicated ways of counting. So we got a little improvement, this square root n, and in 1973 or 74, Piff improved this bound even more. what he used was a way to describe a matroid on n elements with few sets. So here's an easy lemma that tells you a characterization of dependent sets of a matroid. The set X is dependent if and only if there's some circuit contained in it, if and only if closure of that circuit intersects the set has a cardinality which is greater than the rank of the circuit. Right, that's at least going down is easy, and then going up is also easy. So this means that if I give you the list of pairs of the closure of a circuit and its rank, then with the list in your hand you can separate out dependent sets from independent sets, because you would just go through the list and see whether one of these pairs points out the dependency. Yeah, is this clear? So you would have a description of your matroids right there. Now the key point is that
that third bullet point.
Sorry?
Should that be a greater than or equal to? Sorry, I'm just trying to press it.
Greater or equal to?
If the matroid just consists of a circuit.
Yeah. Where you want greater or equal here?
Yeah, maybe.
I want to prove dependency, yeah? So this closure here is just a flat. Now you're saying my set intersects a flat, and the intersection with the flat is bigger than the rank of the flat. Well, then in the intersection there must be some dependency.
If it was size on the right, it would be greater than or equal to.
Oh.
It is obvious after all.
It must be.
Take your time, take your time.
Sorry.
Yeah, all clear?
Could that be wiped from the YouTube record?
I'm sure. Okay, so the next point I need to make is that this description is a short description. Right? Because if the description is short, well, there's going to be few short descriptions, and that will then give you an upper bound on the number. So short in this case will be the cardinality of that set, which completely describes my matroid, is at most 2 to the power n plus 1 divided by n plus 1. And the proof is math. So what you do is you count the number of closures of circuits by considering the map that takes a set to its closure. And what you see is that the circuit, if you have a circuit C, then C minus E, the closure of C minus E is equal to the closure of C, right? Because that one element is going to be spanned by the rest of the elements. So this map takes each of these sets, cardinality C sets, to that same closure. And now if I consider the circuits of a certain size, or a certain rank I, then all the I sets from n, if I take all the images, then I'm going to see all the circuits, and in fact I'm going to see the closure of circuits I plus 1 times. So this then gives you an upper bound on the number of closures of circuits of a certain rank. And then to get the upper bound on this k of m, I have to sum over all the possible ranks that I can get. And then, yeah, here's a little combinatorial thingy that n choose I divided by I plus 1 just equals n plus 1 choose I plus 1 divided by n plus 1. Now, this is a lot easier to add. You just all the binomial coefficients add up to 2 to the power of n plus 1 at most. Yeah? So, well, the upper bound now follows by considering that since each matroid is described by one of these k, and these k's are subsets of 2 to the power e times, well, the numbers 1 up to n plus 1, well, I can just count those. I know that the set I'm taking these k from has this size, and I know that the k that describes my matroid has a size at most this, so I have to sum over all possible sizes between 0 and that, this binomial coefficient, and thank goodness there is a nice expression for that. I mean, this is a good upper bound, and if you just plug in these numbers, you'll get this. You plug in these numbers and take the logarithm. So when you take this logarithm, this k is going to be up front. It's k times logarithm of this. And as you can see, what is my k here? Well, it's this upper bound on the size. And this 2 to the power n divided by n more or less is in there. 2 to the power n divided by n. And then the logarithm of this here will be something of order n. It's just the logarithm of some small power of n that you end up having. Yeah? Because you're comparing the size of this set, so it's 2 to the n times n plus 1 with the size of this set. So if you divide these, you get something like n squared. Yeah? So that's a good trick. We'll use it again later, making even more compact representations. But for now, I'm still in 1973, and I want to. We're a little better now. It's 2 to the power n divided by n times log n. So before it was 1 over square root of n. So we've improved, but by a small margin. And the question is, so this is not going very quickly. The question is, are we going to be home before the end of the century if we go on like this? So what we need is a lower bound, telling you how far we're really off from the truth. And in 1974, Knuth made a lower bound. Before that, several people tried, and they came up with rather weak answers. If you consider the truth. So let's first make some weak attempts. I mean, the obvious way to make a lower bound on a number of matroids is just consider some nice big class of matroids. And, well, what kind of classes? Things that come to mind, well, perhaps graphic matroids. So, I'm not going to work very hard to make an upper bound here, right? My upper bound on a number of graphic matroids is, well, I just consider some set of n plus 1 points, and there's n plus 1 choose 2 possible edges I can plonk in there, and then on n elements I choose n of them. So that's my upper bound. If I take the logarithm of that, I get something of the order n log n, which is not exactly up there with 2 to the power n log n over n, which is really close to 2 to the n. So, another attempt, perhaps it's binary matroids. It's even easier here to make an upper bound. It's a weak upper bound, you can do a lot better than this, but now there's 2 to the n possible vectors in a space of dimension n. You need n of them, so 2 to the power n squared, logarithm is n squared. Still horrible.
Do we know that a binary matroid has a trivial automorphism group?
Yes.
Okay.
On average.
Yeah.
Is this
Well, I'm just first doing, you're thinking of lower bounds.
No,
I'm
just
first doing sort of a
it's just
feasibility check.
it's just an
right?
aside.
I'm making an upper bound to see
Yeah.
whether it's possible at all to get a good lower bound. Indeed, if the answer were yes, then I would have to consider this automorphism group, right? I couldn't just create them and say, oh, now I have so many. You overcreate them. But it's not going to happen with these binary matroids. And G of Q representable, well, same thing, except that you now have a log Q, which is still not going to help much. Transversal matroids. I think every transversal matroid is characterized as the transversal matroid of a set system with n sets. So you would have to specify n sets, and subsets of an n set, and take n of them. So that's this, again, about n squared. All of these are really easy upper bounds. There's also the real representable matroids, and making upper bounds for those is much harder. But it was done by Noga Alon in 1986. But then you get something like n to the third. It's a bit sharper, but I'm not writing down the exact expression. So, no way. We need something else, and fortunately in 1970 Henry was also enumerating matroids on 8 elements. So, what he found was that if you enumerate matroids on 8 elements, the majority of them are paving matroids. Paving matroids being matroids such that each circuit has a size which is at least a rank. So there's only 2 types of circuits now. Circuits of size rank +1 and circuits of size rank. No deep dependencies here. And they dominate the set of matroids in 8 elements, and Gordon and Dillon, they enumerated matroids on 9 elements, and it's even worse there. I think 76% of the matroids are paving matroids. Sparse paving.
I thought it was even higher, but okay. Yeah.
I think paving is higher, and then sparse paving is
That's what I'm
76%.
thinking.
Because what are sparse paving matroids? Well, they are the matroids that are both, so that, well, the matroid and its dual are both paving. So you don't have small dependencies, you don't have small codependencies. And I'll consider sparse paving matroids because if it were true that asymptotically all matroids are paving, then asymptotically all matroids are going to be paving and co-paving, so sparse paving. So, well, I don't have a good upper bound on sparse paving matroids yet, so they seem a likely class to give a lower bound. Now, how do you create a sparse paving matroid? Well, what you need to realize is that sparse paving matroids correspond one-to-one with stable sets in the Johnson graph. So the Johnson graph is the graph whose vertex set is all the R sets from your ground set E. And 2 R sets are going to be adjacent if their symmetric difference is 2. You go from one to the other by throwing out something and adding something. So now here's a nice picture of the Johnson graph for a ground set of size 4, where you consider all the 2 sets. So each vertex shows the subset of 2 elements by just indicating them in black, I guess, or the other ones. That's right. I stole this picture from Jorn. That's very nice. So the thing is, if you take a stable set in the Johnson graph and then use its complement in a set of R sets from E as the base set of a matroid, you'll get a sparse paving matroid, and vice versa. So, making only a stable set of the Johnson graph dependent is a nice way to satisfy the base exchange axiom. Because if the base exchange axiom is not satisfied for a matroid, you're going to have 2 bases, so that, and there's going to be an element somewhere in one of the differences, so that whichever way you try to exchange this element with something in the other, draw something. So if base exchange is not satisfied, then you will have one basis, another basis, there's some E here, and whichever way you try to exchange this with some F, it's not going to give you another basis. But that means that exchanging E with F, you get a dependent set, and exchanging E with F prime gives you a dependent set. And these 2 dependent sets are very close. The intersection of the 2 is, well, all of B minus E. So that cannot happen if you chose your dependent set, stable set of the Johnson graph. So if you don't, well, that of course proves only one implication, but if you're not too worried about the other implications. So this is a great way to generate a lot of matroids. You just pick a stable set, choose those R sets as the dependent R sets. So now we need a good lower bound for the number of stable sets of the Johnson graph. Well, I give some names here to the number of stable sparse paving matroids, and the number of sparse paving matroids on ground set N of rank R just equals the number of stable sets of J. So now how about this lower bound on S and R? Well, Knut had a way to make a lower bound, and I'm not doing him justice exactly by writing his theorem like this, because it's more or less, it sort of trivializes what he did, but after you realize that the Johnson graph, the stable sets in the Johnson graph give you sparse paving matroids, this is essentially the only thing you need to do. You have to realize that the number of number of stable sets in the Johnson graph, or the logarithm of that, is at least the size of the largest stable set in the Johnson graph. Because if you have a stable set in any graph, all the subsets of this stable set are going to be stable sets themselves. So if you have a large one, then 2 to the power the cardinality of the large one is a lower bound, and taking logarithms, the size of the largest stable set is a lower bound for the logarithm. And so what you need now is one very big stable set in the Johnson graph. And people knew some way to construct them. In 1973 they had a way to construct a stable set of this cardinality. So you could take, so this is for the Johnson graph where R is about half n, and is 1 over 2n fraction of points they could get, which was a stable set. Now this is great, of course. You get a lower bound on S and R, or Sn, which is of this order, and this is getting close to the upper bound of PIF already, which is also binomial coefficient times log n divided by n. It's getting close, but it's not quite. Not quite. Actually, the lower bound gets a bit better in 1980 because Graham and Sloan found a better way to create a large stable set in the Johnson graph. And the proof of that is so nice that I just want to give it. So here's the construction of a set of stable sets of the Johnson graph. So each of these S and Rk is going to be a stable set in the Johnson graph J and R. So the elements, the R set from the set 1 up to n, well, this is just a set of numbers. So you could add these numbers and take the result mod n. And this is going to be a stable set. And now I can reuse this picture.
You mean the ones with a fixed sum?
Fixed sum. Yes.
No.
Yes.
The k.
Yes. Fixed sum is k. Because if you have two R sets called B and B prime, for bad reasons, then what happens to this sum mod k when you go from one to the other? Well, you're throwing out E, so you do minus E, you're putting in F, so you add F. Now, these are two distinct elements from 1 up to n, so their difference is distinct from 0. And so this guy has a different sum mod k than this guy. Well, and that's all the possible adjacencies that you have in the Johnson graph. So adjacent R sets are not going to have the same sum mod k. So limit yourself to a fixed sum of k, then it's a stable set.
So,
Now, sorry?
that's right. So this is all based on finding one large independent set.
Yes.
Yeah. Wouldn't it be better to find two?
Well, you could still have a large overlap, huh?
Yes.
It's actually very
Yes.
difficult to increase that lower bound.
Yeah.
But it's yeah, we can do something, but it's not great. You just can make very minor improvements.
So this gives a coloring of the Johnson graph, right?
This gives you coloring.
Is
yes.
it the best coloring?
I think for some Johnson graphs you can do with one less color. So the color number is one lower. I think a lower bound is n minus 1. And then there's a few small ones that have n minus 1. I have to look it up.
Is there a result in the size of the largest possible stable set in the Johnson graph?
Yes, but I have some bad news about that. But I'll talk about this later. Well, okay, so it's the coloring. One of the color classes is going to, with n color classes, one of them is going to have this size. And so this is the best lower bound on the number of sparse paving matroids, and then on the number of matroids that we have at this point. So that was 1980 at most. And then in the last 2 or 3 years, Jorn and myself and Michiel Bansal worked on finding better upper bounds. And yeah, this is sort of a peculiar list, because it's essentially the same theorem, except that the bound gets better and better. So you may wonder why we're still bothering with these two when this is clearly the winner. But my reason for that is I'm going to explain you a bit more about these two results. Point one, they're easier to prove, so you can really understand them completely, just in half an hour. The other thing is these two techniques that we use here are more flexible than this one. So this is of course the winner for counting all matroids, but the techniques we used for counting them here also apply to other, say, minor closed classes or matroids with a certain property, simply because they're simpler techniques, so they're easier to tweak. And there's yeah, a bit more homogeneous somehow. With this technique, it's really very hard to use extra properties of the matroids. But Jorn is going to explain more about this result and extensions of that. And right now I'm going to give you short counts of the proofs of these two results. So the first of these theorem really has a proof that is very close to the proof you've seen by Piff. It takes some compressed representation of the matroid, just some set system, so that if you know the set system, you know everything about the matroid, then you show that there's few of those compressed representations and hence few matroids. So I don't need to give you, well, that's what's on this slide. So what we have so far is this lower bound by Knuth, and this upper bound by Piff, and then as you can see, this is getting a bit better because we replaced the 2 to the power n by this binomial coefficient, which is square root n better. And indeed, we do it just like Piff. We make some compressed representation, which we call a cover of the matroid, and then the size of this cover is going to be of this order, and then you count the number of those covers. And really that part of the proof is identical to what you've already seen. And you may note that this log n divided by n times n choose n over 2, well, it's exactly this, except that you've picked up an extra log factor, which comes from the application of this upper bound as before. Yeah? So I'm only going to explain what these covers are and why you have covers of this size, and then you can just, the rest is identical to Piff's proof. So what is a cover? Well, if use the fact that if you want to certify that some set is dependent, you could use some flat of the matroid for that, right? If you have a flat of the matroid and the intersection with x has a cardinality greater than the rank of the flat, then having the flat and its rank is your certificate that x is dependent. And what PIF did was collect such certificates for all possible dependent sets. What we're going to do is collect such certificates only for the R sets, which greatly helps. Because the way PIF did it, when you think about it for a minute, if you want to collect certificates like that for all possible dependent sets, well, you better include all the closures of circuits, right? Because you want to show that certain circuits are dependent. And then the next thing you realize that once you have all the closures of the circuits, you don't need anything else. So PIF just had one choice of set system for this compressed representation. But the interesting thing is that if you, of course, if you can separate out the dependent R sets from the independent R sets, then you also know the matroids. And then all of a sudden, there's more than one possibility for creating such a list of certificates. So I had a little definition here saying that some set of flat covers a subset of the power set if for each dependent set in that subset you have a certificate like this. And now the object is, if you call this covering, now the object is to have a set of flats covering all the R sets. Now what I want is a cover of this size, and just counting the number of such covers is then giving my bound. So what I do is two things. I consider the Johnson graph just as a d-regular graph, and so what is the degree of the Johnson graph J and R? Well, if you have an R set, then how can you go to a neighbor? You have to pick somebody to throw out, and you have to pick somebody to add in. So you have R choices for the guy to throw out, and you have n minus R choices for the element to add, and so that the Johnson graph is regular of degree R times n minus R. Now any d-regular graph is going to have a dominating set of a cardinality at most this. So where this is just the number of vertices of the graph. And a dominating set is a set of vertices so that each vertex of the graph is either in the set or a neighbor of an element of the set. Now, this is an old result. One way to prove it would be to consider a random subset of vertices of this cardinality, and then you can, well, it's sort of it's just an exercise to show that in expectation you're going to see all the vertices of the graph in the set or in the neighborhood of the set, except possibly so many vertices. Now, there's going to be some set that beats this expectation. You pick such a set and you just throw in all the other ones to complete your dominating set. And it's sort of a shame that we don't have anything better for the Johnson graph, which is a highly structured object. But, we asked Andries Brouwer, and he looked very worried. But at that time, we were still needing a better upper bound to improve our results. And yeah, this is just terrible. People tried and failed. And did so for many decades. So, but anyway, it's good enough for now. So now we have a dominating set. So we're good. So if this is all the R sets, we now have a set of vertices, and together all those neighbors neighborhoods cover the entire set of R sets. So we're good if we know a way to cover all the R sets in the neighborhood of a fixed set with few flats. And we can. If you take any X, any R set, then you can make a set ZX covering, well, that set itself and its neighborhood of a size which is at most, well, the minimum of R and n minus R. Well, I can show you which set to take. So what you can do is take Zx equal to the set of closures in the matroid of x minus x, little x for all little x in x. And then if y, which is x minus x plus y, is a dependent set, then it's going to be covered by the closure of x minus little x. Now, since x itself has only R members, this is a cover of cardinality R. And so this will do it to prove the upper bound of R, and the dual argument will give you the upper bound of n minus R. So, now, to get a cover of the entire set, we just take the union of all these guys, and to get an upper bound on the cardinality of the union, you just need to multiply this upper bound with the number of elements in my dominating set. And if you just work this out, you get where the 10 is just some generous constant to get rid of, well, things that happen for n very low. Yeah? So the proof really uses some, well, this is a strange element in the proof, that you use this dominating set. There's more than one way to create it, but they all involve some kind of randomization. So here you created this dominating set by randomization, but you can also do it more or less directly.
So how small do you think that dominating set should be? Is it that boundary bad?
Well, we know that there's Pendavingh matroids with at least n choose R over n circuit hyperplanes, so dependent R sets. And the cover that I'm creating here would have to have an entry for each one of these for each one of these dependent R sets. Because they're isolated, a flat essentially could just point out one of them, and then it can't say anything about the other guys. So I know that there's going to exist matroids with, so that the smallest cover have a cardinality, well, which is bound from below by the Copeland number of the Johnson graph, which is just a factor of log n away from this upper bound.
Right, so for the dominating set.
Now look, this is the upper bound I have for my...
No, sorry, I was asking about the dominating set.
Oh, for the dominating set.
Yeah. So that maybe it's given it's
So people have no better upper bound, but for lower bound?
Well, there's a standard lower bound that is just a 1 over d plus 1.
Yeah, yeah.
Divergence.
Yeah, I mean, each one of these neighborhoods has only d plus 1
so like
member,
have you done some
so
computations that
I
tells
need
you
at
what
least...
the,
Sorry?
have you done some computation to see what that number should be? For the smallest size of the dominating set?
No, I haven't. Have you seen any...
No, I don't think we've ever tried that.
But clearly there's the lower bound is this, because each
Right,
one of those
yes.
neighborhoods is just picking up d plus 1, so you just need a 1 over d plus 1 fraction at least.
So what's closer, that obvious lower bound or that probabilistic upper bound?
We don't know. Yeah. Okay, so this actually it's really very close to Pith, but this is all by hindsight. We first had a completely different argument working with circuits and co-circuits together forming this certificate. But you know, when you after reworking it a bit, it's really just a minor adaptation of what PIF does, and well, a trick for creating this short certificate. Now, after a few months or so, well, we were of course unhappy with the fact that there was still this log n squared in there, and in the real upper bound. Here's just one log n, but there was log n squared in the upper bound for the number of matroids. And so we tried hard to improve this, and we did. So we got this last theorem, and after we found that one, we found a worse theorem with a very simple proof, which is this one, and it's really very enjoyable. So here's a very general counting principle. Suppose I want to count the number of elements in a certain set W, and this W is taken from the power set of U. So it's just a bunch of subsets of U. Then to make an upper bound, I can consider a partition of U. And to now bound the number of elements of U, I can just count for each element of my partition the number of subsets that are induced in these Ti. So I can add notation, Wt is just a restriction of my set W to T. You take all the intersections of elements of W with T. Now clearly, the number of elements in W is bounded from above by the product of the number of elements in these restrictions. Because, well, if you just consider how an element from W can look like, well, you can reconstruct it by piecing together a set from Wt1 and putting it next to a set from Wt2, and if you do it in all possible ways, then you'll quite possibly get more than what you started out with, but certainly not less. And so this should be completely simple. So if is it clear? Now, you can very often use this argument, but sometimes you don't have complete control on the kind of sets T for which you have accurate counts. So it can happen that there are certain subsets for which you can make counts, but they don't form a nice partition. And then there is this argument of Shearer that comes in very handy. So you have a thing about entropy, and I'm not going to. I didn't want to talk about entropy, which is it's just another set of definitions. But one consequence of Shearer's entropy lemma, so a reformulation almost, is that if I give you a set of sets T1 up to Tn, and this time it's not a partition of U, but each element of U occurs in at least K, so it's a K cover of U, then you get the same upper bound, but now with cardinality of W to the power K here.
Is there a combinatorial proof of that, or do you need to use the Martian entropy?
I need to use the Martian entropy. I think you can do it with Hölder inequalities, which is not exactly combinatorial either. But the entropy proof is just fantastic. Right? If you have a half day, then you learn the definition of entropy, and you just there's a great paper by Bolo Bash and another author, which is fairly recent, about Shearer's entropy lemma. So now we're going to apply this to count matroids. We're going to prove this theorem, saying that if you take the logarithm of 1 plus the number of matroids on n elements of rank R divided by n choose R, this is at most the logarithm of 1 plus the number of matroids, where these two numbers are decreased by t divided by that same binomial coefficient, again decreased by t. And you can see I have an n prime here, because my lemma applies to numbers of matroids in contraction closed classes. Actually, the whole set of matroids is contraction closed, so I can apply it to that later. So to apply this theorem above, to get this result, well, I want to count the number of matroids. So what I'll do is I need to identify my matroids with subsets of some big set. So the big set is going to be all the R sets from the ground set, and then my matroid is characterized by listing its bases. And this is a subset of that, all the R sets from E. And of course, I want the base set of a matroid in my contraction closed class here, eh? Not that because I want to count them. Now, so I want to apply this lemma here. So the other ingredient is sets ti, where I can make a count. And so what I'll do is I'll consider ts for all possible t sets from E. And then ts is all the R sets containing S. Now, when you restrict your attention to all the R sets containing a certain S, you're essentially looking at the matroid you get by contracting S. And so, an upper bound for this number will be, well, the number of matroids in your set with t less elements and rank R minus t. And, well, the rest is just, you know, working out the details of this, because you have to consider how many times an X set is now containing one of these S's. Well, that's going to give you your K, and the rest is just, you know, elementary stuff. You may wonder why this 1 is coming up in this lemma. Well, the thing is, I'm considering sets B satisfying base exchange, and the empty set, of course, satisfies base exchange. And I need the empty set in there because if the S I chose here is such that it's dependent in matroid, then I'm not really contracting it, I'm just getting the empty set as a result of this contraction. So I want it in my set, because otherwise my counts will be off. Clear? More or less clear? So now, so this is just repeating the lemma that I had. Now, if you want to prove an upper bound on the number of matroids, what you do is you apply the lemma and choose your t so that this fraction here refers to matroids of rank 2. And now it's easy to count matroids of rank 2, right? They just characterized by partition, parallel classes instead of loops. And if you just plug in that upper bound here, well, this gives you an upper bound for this logarithm divided by n choose r. And of course, I want an upper bound on all of these, but this is trivial stuff. This is the hard part. No? Now, the nice thing about this, in particular, this lemma here, is that you can use it to bound contraction closed classes, like the set of matroids not containing a certain minor. And all you need to do to make this whole thing work is to get a good bound in a low fixed rank. Well, that's not how we did our paper on counting matroids in minor closed classes, but we later found that we can actually use this lemma and do everything that's in there. So, here's a list of conjectures about the asymptotic properties of matroids. Well, you say that asymptotically almost all matroids have a certain property. Well, exactly when you think you want to say this, namely that if you count the number of matroids with that property and compare it to the count of all matroids on the element, then the limit as n goes to infinity tends to 1. Now, I think Dylan and Jeff and Mike Newman, Dominic Welch formulated a few conjectures. And I think, so they were conjectures that were more or less, not all of them are really your conjectures, I think, huh? Or are they, so how, what
Well,
what's going on when you
asymptotically
formulate
almost all
it?
matroids as sparse paving is a Henry conjecture. So
Yes, yes, but
my recollection is we thought, we tried to find some things that were obviously true that we could prove.
yeah.
You found some
These
things that
are
were
things
obviously
that
true that you couldn't
we
prove.
prove. Yeah.
Well, I certainly love that you put in those conjectures because they're sort of now my reference point for all this work, because it's certainly a very nice list. So I guess this is the mother of all conjectures, but most of these statements are more or less independent, except perhaps the statement about K connectivity. It's easy to show that sparse paving matroids are K connected when n is greater than K or something, or the rank and the co-rank are both greater than K. So this, if you would have that, this would follow. But for the others, there's still some. Well, you could prove this without showing these other two. Yes. So I'll discuss these 4 conjectures in the next few slides. In fact, Jorn is going to talk more about these, and I'll say a few words about these two. So the first conjecture was that if n is a fixed sparse paving matroid, then asymptotically almost all matroids have n as a minor. Now clearly, if you believe that almost all matroids are sparse paving, this is not going to be true for a non-sparse paving matroid, because the sparse paving matroids are minor clause, so if you pick somebody outside that set, and the sparse paving matrix is everything, that's not true. But then still the question is, when you take your n inside the set, will it be a minor of every possible matroid, every possible sparse paving matroid? Well, I'm not so sure about that statement as I perhaps was, but there's something on the positive side and the negative side. I think Jorn spoke about it in Princeton. So we have this theorem, which is just saying that the conjecture is true if n is one of these matroids here, either a k-point line, U36, P6, Q6, or R6. So in the paper we wrote about this, we used something called cover complexity, which is essentially an adaptation of the first argument for counting matroids. So it's perhaps nice to show how you do it using this entropy lemma. And at first I thought it wouldn't be possible, but the thing is, if you apply this entropy lemma, let me just go back to that slide. Okay, so here's the lemma. Suppose now you want to count matroids without a k-point line. If you do it exactly like this, go down to rank k, then rank 2, yes, thank you. Then in rank 2, this gets somewhat better. The number of matroids without a k-point minor is, I guess, k to the power n, most. Because you have to choose for each one of your elements in which parallel class is going to sit. So you would get n log k upon taking the logarithm. That's not good enough. It's going to get you rid of this log factor, but that's not strong enough to prove that this upper bound you get is not much lower than Knud's lower bound. So we thought that it wouldn't be possible. But in fact, when you go to rank 3, there is a good argument. Because matroids of rank 3 without a k-point line, well, if you simplify them, there's a certain constant upper bound for the number of points that you can have, k squared. Now, if you start counting those matroids, you say, well, I choose, so you're going to have a constant number of simple matroids without a k-point line in rank 3. So to make a count, you say, well, I choose one of these constant simplifications, then I have to choose for each one of my elements to which parallel class it's going to belong, and so you will have k squared to the power n, which is essentially the same upper bound we got in rank 2. But now it's rank 3, and now it compares very well to this n choose 3 here. And then all of a sudden you have an upper bound that tells you that almost nobody is going to be k-point line free. And in fact, the same argument applies to U36, P6, Q6, and R6, but you need some, well, you just need a lemma saying in rank 3 there's going to be just so many elements, or so many matroids without U36 say. Actually, the lemma for U36 is quite nice. Turns out that if you have a simple matroid of rank 3 without a U36 minor, and it has sufficiently many points, then it has to look like this. And so there's not so many of those. So you'll have the small ones, you'll have these, you count them, and the bound is good enough. Now, do I believe this conjecture? Well, I don't.
You don't, or you don't know?
Sorry?
Did you say I don't, or did you say I don't know?
I don't believe the conjecture.
Okay.
But I don't have proof, but I have some negative evidence. Because I can construct sparse paving matroids and elements without an MK4 minor in these numbers. So this is just Knud's lower bound on the number of all sparse paving matroids, and I can get arbitrarily close to that. I can essentially show that if n is even, or if n is odd, then all the sparse paving matroids created by the construction that I showed you will not have a K4 minor.
But then, so you're saying you believe that Muth's constructions account for almost all sparse paving matroids?
No, that's not why I believe it.
But you could have that asymptotically almost all sparse paving matroids with sparse paving matroids, where sparse paving matroids is some property within sparse paving matroids,
Yes.
that was sort of minor closed. And if you had that,
Oh yeah,
you'd have that the conjecture was false. Right?
well, that
and
I
that's
certainly,
I'm
certainly
starting to
believe.
believe something like that. Right?
Yeah, I would certainly believe something like that, but I don't believe that Knud's or Graham and Sloan's construction points out exactly those sparse paving matroids. There's more going on, and we don't have the overview. There can be really many different classes, but it's going to be more structured somehow. We don't know the structure, but yeah. Yeah. And about connectivity, well, it's very frustrating because this really should be true, right? Sometimes almost all matroids are K-connected. This is just true, except we don't know why.
Shoot me if it's false, right? Shoot me if it's false. If that was false.
Shoot all of us. That's false. Well, I guess that in the same paper where you put all these conjectures, you proved it.
Not quite, actually.
No, it was something
No, they
weak
didn't prove
result.
that one.
Sorry?
Yeah. No, they didn't prove that.
No, they
They
didn't.
proved that the probability was greater than a half.
You might be able to
yeah,
guess
yeah.
who did prove that theorem from the
Oh, but you're right,
objections
yeah.
that are coming from the audience.
No.
From the audience feedback, you might be able to guess who did prove the theorem.
Well, actually, you proved 3 connectivity.
Yeah, we did 3 connectivity.
That's correct.
But we also did the previous one as well.
Yeah. Okay.
Yeah, I mean, quite, but you know.
But then you still hold the crown because I can't do anything. Well, I can't prove this for connectivity or K connectivity.
No.
We can do something, by the way, for K connectivity. When we show that asymptotically almost all matroids on n elements have no K separations where both sides are big, where big is bigger than log squared n. And for that we can apply this entropy method. But that's not good enough.
That bound doesn't depend on K though, does it? If it depended on K and not N, then you'd have proof that asymptotically almost every matroid was F connected.
It doesn't depend on K.
So the C log squared N, if that was a function of K and not of N, that would be nice.
But it is a function of n.
Sorry, say that again?
So it is a function of n, right? That's
Yes,
log n.
I'm saying if
It was a function of K, is what John's saying.
what I'm really saying is, if you had a different theorem, it would be very nice.
Yeah, I agree. I can only agree to.
Non-controversial statement.
Actually, I'd like to talk to you about this because there may be complementary things here. I mean, you would think that small separation. So in your paper, you also separate out this kind of K separation or 3 separations from ones where one side is small.
Yeah.
So perhaps there's still something you can do to deal with the other half of this statement.
If you had a much sharper estimate for how many matroids there are on the small side of the separation, would this theorem be better? Is it the interaction across the separation,
It's
or
the
the
interaction
stuff on
across the
yeah.
separation that's the new element. Actually, we can do something about that, but it's too detailed to do it now. But I'm happy to sit down and talk about that later. But I think we should give Jorn the floor because it's getting warmer. And after you heard what he has to say, you'll be even warmer.
Can you go back to the slide about the no K4 minor, please, and just show me it again? Because okay, just want to copy that down.
Thank you, Rudi.